Hi everyone, this video will go through some exam questions on the photoelectric effect. Now this topic is considered one of the most difficult in Physics A-level, so you will have to work hard, do persist, and hopefully by the end of this lesson you will be aiming at that, achieving at that A-star level. Okay, so these are the three questions that I've selected. The first question is your standard question, that's probably your grade C level. Question 2 is a bit more difficult, and then question 3 will be the high grade question, the grade A-star. This should be the data and the formula that you need. So I recommend you pause the video, get a paper, pen and calculator. You might need to spend 20 minutes, possibly longer, working through these. When you're ready, press play and check your answers. Right, here we go. So we've got the work function for metal is 5 eV. We need to find the minimum frequency needed to remove the electrons by the photoelectric effect. So the minimum frequency, also known as the threshold frequency. Now, before we go into the calculations, we need to look at this formula. So we've got, as we saw last lesson, the energy of the photon is equal to the work function plus the max Ke. That max is really important. But we define threshold frequency as the minimum frequency needed to just release electrons to the surface of the metal with 0 Ke. That's really important. There is no excess energy. So if the Ke is going to be 0, this simplifies this formula quite significantly. And we can just get rid of the Ke max. So we end up with HF is equal to the work function. Now sometimes we put a little dash here or a little note to remind ourselves that this is not just any old frequency, this is specifically the threshold frequency. So we end up with a far simpler version of the original equation, and we can make F or F dash the subject. That's equal to the work function divided by the Planck constant. So this becomes substantially easier. However, we need to make sure that we are in joules. So very often a question will give you energy in EV, and we saw in previous videos to convert EV into joules, we need to multiply by elementary charge, 1.6 10 to the minus 19. So that's probably why this is 3 marks rather than 2, because we have this extra stage here. So always remember we need to be in joules, not EV, for calculations with this formula here. Right, that says part C, that should be part B. So this is a more standard question where we actually have to find the kinetic energy and then the velocity. So we take our formula here and we make Ke or Ke max the subject. So we subtract 5 from both sides. So we have HF, which we can calculate. So Planck constant multiplied by the frequency we're given. Take away the work function as we did before in joules, so multiply by 5 by 1.6 10 to the minus 19. And we should end up with a positive value, and it should be a really tiny value as expected. So 10 to the minus 19 sounds about right. Just be careful here. Very often students will calculate that and think that's the end of the question. And other questions may have said calculate Ke max. But in this case, it says find the maximum velocity. So we know that kinetic energy is equal to half mv squared. So to make v the subject, rearrange root 2 Ke, that's divided by 2. That should be divided by m, I think. A typo there. So we put in our values from before, and we should get this velocity here. That's going to be 1.1 10 to the 6. So a few comments on this. The first one is expect a large velocity. So electrons, because they have such a tiny mass, when they move very, very quickly. So if you get a velocity of an electron as 5 meters per second or 2,000 meters per second, it's not necessarily incorrect, but it probably will be. So expect 10 to the 5, 10 to the 6, or even higher in terms of your velocity. Another key exam tip we could add to this is show your working out. So if you just write an answer with very little or incomprehensible working out, you'll get no marks whatsoever. However, if you show all your working out and get the wrong answer, hopefully you'll get 1 or 2 marks for your working out, which demonstrates you understand it, even though you might have made a mathematical mistake. Question 2. So this refers to a photocell circuit. Now, the previous video did talk about how this worked, but we can have a quick recap. In essence, it's very simple. So rather than just have the gold leaf electroscope, where we can see electrons being released by the gold leaf foil falling back to the vertical, in this case, we can actually make measurements of how many electrons are released. So we have the UV light shining its light onto a target metal, and electrons are being released from the target metal and then making their way across to the other plate. And we have billions and billions of electrons doing this. So as they move around the circuit, we can detect a current. So this is what we're trying to find here, the maximum current. So I would say this is a grade AB type question. It's a bit more difficult. So we've got 15 watts, which is joules per second. We've got photons in EV, so we're going to have to convert that to joules. And then we need to think about current, so Q over T. So this is definitely a more difficult question. So the first thing we can find is the energy of the photons. That's going to be straightforward. So even if you cannot answer anything else, convert EV into joules. You should be able to do that. We multiply by 1.6 10 to the minus 19, and we get this tiny value in joules. So that's the energy of an individual photon. Right, so what do we do then? We're given power. So if you ever get a question where you think, I don't know how to progress through this, write out a formula. Write out the formula for power. You're given that in the formula booklet. You know that from GCSE. P is equal to E over T. Now, there's different ways we can approach this. We can either look at the units, and we'll come to that tip in a moment, or we can just think, well, what's actually happening? If I want the photons per second, now photons is not a unit, so I want something per second. What I want is 1 over T. So if you rearrange this to make 1 over T the subject, 1 over T is equal to P over E. And then we divide the power of 15 by the energy of an individual photon. Now that's not intuitive at all. And even though we have this formula, that may not make a lot of sense to you. There's various things we can think about to help us understand this. One is to look at the units. So we know the units of power are watts, and 1 watt is 1 joule per second. So I could write 15 joules per second. And I know that the energy of a photon is joules. So if I divide joules per second by joules, the joules cancel and I end up with s to the minus 1, which is, as we need this for energy per second, the photons per second, s to the minus 1. The other way of thinking about this is we expect to get a really big number of photons, and the only real sensible way we can combine these two numbers together to give us a big number is 15 divided by the tiny number of joules. So this step here is not intuitive. It's not necessarily clear how to do this with P equals E over T, but this is something you need to be able to do, calculating the number of photons per second. Right, so we have the number of photons per second. So what do we do with that to find the maximum current? So it says the maximum because we assume that every single photon has a one-to-one interaction with an electron, produces this electron, and then that's detected by the emitter over here. So that's the maximum. In reality, it might be less because some of the photons will not release electrons from the metal. Mathematically, this final stage is quite straightforward, but once again, you could get really confused with how to use these numbers. So your starting point would be to write down the formula for current, I equals Q over T. If we're thinking about one electron, we know the electron has a charge of 1.6 10 to the minus 19, and the number of electrons per second will be the same as the number of photons per second, because we assume that every photon produces 1 electron. So I can use this number here. Even though this is photons per second, this is also going to be electrons per second. And if I multiply these two numbers together, then I'll get coulombs per second, which is amps. I'll also get a sensible number of currents. 2.8 sounds about right. So again, it's the only sensible way to combine these two numbers, which will give me a current. So this is quite a difficult question. Mathematically, there are only 3 relatively straightforward calculations, but we need to be confident how to combine these numbers together in order to give us Q over T, coulombs per second, which is amps. Right, question 3. So I think this is a grade A, probably a grade A star question. It's really drilling down to your understanding of photocell circuit, number of electrons, number of photons. There's a lot of terminology. And then there's also understanding what's going on generally and how that relates to what we detect with the circuit. So there's quite a lot going on here. So we did talk about this in the previous tutorial. So We know we're getting electrons produced and they're detected by the ammeter here. And normally we would have the voltage on 0. So we can change this voltage, we can make it positive over this side or negative over that side. And if I make it negative, then these negative electrons that have been released from the plate will start to be repelled by this negative plate here. So the current detected is going to start reducing. So fewer electrons produced, same number of electrons produced, fewer electrons making it all the way to this plate here. So the current, known as the photocurrent, will reduce. Now if I increase that negative PD, if I continue to increase it, at some point, even the fastest electrons, the ones with the biggest Ke, will not make it all the way to the negative plate. So we get a 0 value of current. So this is our answer to part A. Explain why the current is 0 at the stopping potential. So for 2 marks, we need to say that the electrons are repelled and therefore no electrons make it to the opposite plate. So they're all repelled, even the ones with the biggest Ke, moving the most quickly, are repelled and we get 0 current. Right, part B, why does the current increase to a maximum? So we can see here that it increases up to a maximum value. And then even if we have a positive PD, then the photocurrent doesn't change. So this is really getting you to think about what is the relationship between the current, the PD, the maximum Ke, all these things. So this is a really difficult question. So there's been no mention here of changing the light intensity. The light intensity gives us the number of photons per second. So that is fixed. The number of photons, or the frequency of photon emission, is going to be fixed. Therefore, the frequency of photons emitted, the frequency of electrons emitted from the plate is going to be fixed. So we can make them travel more quickly if I make this plate positive. In fact, they will be traveling more quickly, but I will not increase the number of electrons produced because the number of electrons depends on the number of photons from the light, and that is fixed. So really difficult ideas. Light intensity is constant and the frequency hasn't changed, so the number of photons is constant. If we have a one-to-one interaction, that means the number of electrons produced per second is constant. Therefore, as we've seen in the previous question, Q over T is constant, so the current is reached its maximum value. Right, here we go on part C. So sketch what will happen to the current if the intensity of light is decreased. So this is really quite tricky. So this is the answer. Now you wouldn't necessarily need to do all these 4 lines, but this does show the trend. So you could probably just do 1 line and label that as lower intensity of light. But what actually happens if we decrease the intensity of light, then the photocurrent, that's the current detected in the photocell circuit, the maximum current will reduce. So all these lines, these horizontal lines will start to move lower down a lower current. However, and very importantly, the stopping potential does not change. So it's not like this x-intercept starts to move to the right. The x-intercept stays constant. Right, so let's think about the explanation for this. So as we saw previously, the lower light intensity means fewer photons produced per second, so fewer electrons are produced per second. So we said the number of photons emitted is related to the number of electrons emitted. Therefore, the current will reduce. So this is similar to what we were saying before, but here we said that light intensity was constant, so the number of photons is constant, so the number of electrons is constant. If we reduce the brightness of the light, we have fewer electrons produced per second because fewer photons are emitted per second from the light. So we can explain why this reduces over here. Why does the stopping potential stay constant? Right, so we said that the maximum energy of the electrons emitted, Ke max, only depends on the frequency of the light shone on the metal. It does not depend on the number of photons per second. That's a really key aspect of an understanding of quantum physics and the behavior of photons, which is why this is a grade A-star question. So just to summarize that, the frequency of light is staying constant, therefore the energy of the photons emitted from the light stays constant. Therefore the maximum Ke of the photoelectrons stays constant, and the stopping potential is related to the maximum Ke. So that is a measure of the energy required to, or the work done to slow down those fastest electrons. Right, some really difficult ideas here, especially question 3. The exam tip I would give you here is as much practice as possible. So the more exam questions you can do, the more exam papers you can do, the more prepared you will be for whatever scenario, whatever contrived example they can throw at you. And however abstract the question, you're going to be prepared because you'll have seen something similar before. So well done for getting through this. I recommend you have a go at the next video, which is wave-particle duality and the de Broglie wavelength, which is quite interesting. So I'll see you then. Bye.